So today the topic, optimality of algorithms. Another important problem in algorithms. When we develop algorithms, the best we can get, optimal algorithms. But most of the time, very hard. People really want to get optimal algorithms, but most of the time, extremely hard. So sometimes we can take, next best thing. Near optimal. May not be, real optimal, but near optimal. People can accept, next best thing. All right. In order to explain this optimality issue, let me use one simple example to explain it. Minimum selection problem, 8.1. All right. First, let me give you the question. Problem number 4. Find the minimum of an array. Very simple question, right? So everyone can do it easily. But from this simple, easy question, we can understand how to get optimality of one. Here, it's a simple one. All right, given an array with this notation, the question, find the index I such that A of I is the minimum of the array. That's simple. Okay? First, let's look at the solution. Solution, pretty straightforward. No trick, no special technique. We can even say we just apply the brute force method. Straightforward, brute force. So let's look at the details. First, the problem type. This is another problem type we call the selection type. Selection type. Okay? I mentioned 3 basic types of problems last time. Search type, selection type, and a sort type. For this class, 3 basic types of problem. All right. So here I give you the reference. All right. The general selection problem. The general selection problem, we will talk about it in our module 4. We will, do more problem solving in the general selection problem. Here, let me give you the problem description first. Find the kth smallest element in a given array. Still given array, but you need to determine this k number, right? First smallest, or second smallest, or third smallest. Just given any k number, you need to find the kth smallest element. That's the general selection problem. All right. But when k equals 1, that's our minimum. Okay? Minimum. 1. All right. Here we are doing the special case, k equals 1. There is another special case, finding the maximum k equals n. Sometimes people call this rank. Rank number. So rank number is 1, 1, 2, 3. Name for this k. All right. Now let's go through the solution. Simple, straightforward. So let's complete that part first. All right. Initialization, when we start, we create a main variable. So this variable is used to store our final solution. But when we start, we need to initialize this variable. So the value of the first element, we use it to initialize this variable. Then we run a for loop. We go through all the elements in this array. the general step. Yeah. In each iteration, we compare this main variable, the value in this main variable, with the value of the current element, main and A of y, and see which one is smaller. Yeah. So we consider two cases. Okay. All right. If main is greater than the value of the current element, strictly greater, then we get a better one because we reduce the value stored in the main variable. So we should update it. Yeah. In this situation, we should update it because we can make it smaller. Yeah. So let's update the main value, the value of the current element, A of I. Yeah, you improve it. Yeah. Otherwise, yeah, so less than or equal to, that means otherwise, you should not update it because you do not get better. Yeah. Our goal, we want to find the global minimum, right? The global minimum. Yeah. But now we improve. So this iteration, we have a chance to improve the value stored in this main variable. All right. So otherwise, we need to do next iteration. Okay? Yeah. Yeah. So the next iteration, we'll keep doing until we reach the last element, I equals n minus 1. When you finish the comparison with the last element, then whatever values stored in main variable, that's your final solution. Because you store the global minimum in that variable. Global minimum. Yeah. You compare the main value with all the elements in the array. And you know that is the smallest. That's the whole algorithm. Right? Yeah. So easy. Yeah. Nothing to argue, right? Yeah. Nothing to argue. Yeah. All right. But the next question, yeah. we find a solution. Then we need to do discussion. Next round, we need to do further discussion. All right. The question. Yeah. First, let's count the number of comparisons we do. We only count number of comparisons. Other operations we do not count. Okay? Because other than comparison, we may have a few other operations, right? Yeah. Later, we call this comparison our basic operation. So we only count the basic operation. For non-basic, we do not count. Okay? All right. The first question. Can you tell me how many comparisons do we need in this algorithm? The simple algorithm?
N minus 1.
Yes, n minus 1. Okay? Do not use n. Yeah. Do not give me n. All right? Yeah, it's very easy. Some students may give me n. The reason is n minus 1 is for the first element, you do assignment. It's not comparison. Okay? So we do not count the first element. It's an assignment operation. Okay? Oh, yeah. Although it's an operation, but we do not count it. We only count comparison operation. So that's why we exclude the first element. Then, for all the remaining elements, there are n minus 1 elements. For each of the remaining elements, we do one comparison. So the total number is n minus 1. Yeah? So this step, pretty easy. Yeah. But now, another question. Yeah. Because every time after we solve one computing problem, we need to ask ourselves, can we do better? Can we improve this algorithm? Yeah. We always need to think about if we can improve it or not. So the next question. Can we do a little better than this one, than this algorithm? Right? Yeah. In other words, is this algorithm optimal? Yeah. If it is optimal, we cannot do better. Nobody can do better, right? Already optimal. Yeah. Yeah. Nobody can do better. Yeah. So here there is an optimality question we need to study. Yeah. All right. Yeah, so here, yeah, so we already, yeah, so yeah, we finished the, the counting. Yeah. All right. Yeah. All right. So here, we can also use counting by reference. Yeah. But here, because it's so easy, so I do not need to elaborate more. Okay. All right. Yeah. We just move to the optimality step. Yeah. Yeah. So here, still I talk about counting by reference. Yeah. Yeah. All right. But let's look at the next question. Is it possible to further improve the algorithm? Yeah. All right. Yeah. So this question, not that easy to answer. Yeah. Two options. There are two possibilities. Yeah. The first possibility, we can improve the algorithm. Yeah. So it is not optimal. We can still improve it. Yeah. Then we should do it. Okay? Yeah. But sometimes you cannot improve it. Yeah. If you cannot improve it, another option you can take. You try to convince people that it is already optimal. This step is hard. Yeah. You need to prove it. Okay? You need to make some convincing arguments to, really apply some rigorous logical reasoning to show it is optimal. Yeah. So this step is very hard. Yeah. All right. Yeah. So here, yeah. So the general process. Now, after we solve a problem, we need to try to improve. Yeah. But if you cannot improve, then you need to consider if it is optimal. Yeah. But show optimality, most of the time it is extremely hard. Yeah. Prove it. Your algorithm is optimal most of the time, extremely hard. Yeah. So then most people, do not do it. Yeah. Do not do it. Because even not optimal, if it is near optimal, still okay, right? Yeah. If it's near optimal, yeah, still good solution. Yeah. All right. Yeah. Optimality. Here. We need to understand this concept, optimality concept. What is the exact meaning of this concept here? Yeah. All right. All right. So why it is hard? Why study this optimality issue is so hard here? Yeah. The hard part. Because in order to show that our current algorithm is optimal, you need to study all the possible algorithms that solve this problem, right? You need to consider, at least you need to consider all the possible algorithms solving this problem. But the questions, how can you access or how can you study all the possible algorithms, right? Yeah. That's the hard part. Yeah. Because nobody can exhaust all the possible algorithms, right? Yeah. You don't know how many algorithms can be used to solve this current computing problem. Nobody knows that. All right? Yeah. All right? Yeah. Yeah. All right. Including unknown algorithms. Yeah. Because when you study all the possible, most of them unknown. Those algorithms have not been developed. Unknown. Yeah. Yeah. But how do you study? How do you study unknown algorithms? That's the hard part, right? How do you study unknown algorithms? Yeah? No. All right. So that's the question. How to study unknown algorithms. Is it possible to study unknown algorithms? Yeah? Based on your intuition, is it possible to study unknown algorithms? Yeah. Possible. Yeah? Good. So many of you feel it's possible to study unknown algorithms. Hard to understand, right? Yeah? Can you say something? Why it's possible to study unknown algorithms? Can you say something?
I was thinking matrix comparisons.
Matrix comparison.
Yeah, like with counting, you have like one matrix is all like numbers, and then another matrix creates your algorithm.
But the algorithm unknown.
Yeah, when you compare, like, this, I compare, like, I go through what all solutions can create these numbers in my matrix solution, and then compare to see which algorithms produce the solutions. It's like, but it would be brute force, right? Very brute force. That's one way of thinking.
Can you say something?
That's what I'm asking.
Yeah. Answer is correct. Yeah. We can study unknown algorithms. Yeah. But the question, how to study? Yeah, we need to know how to study unknown algorithms. Why it's possible. Yeah. All right, let me tell you how to study. Yeah. Yes. Yeah, it's true. But the question, how to study? Yeah, unknown algorithms. Here, there is a commonly used method people can use to study unknown algorithms. So actually, although here we say unknown algorithms, it's not completely unknown, right? Partially known. So partially known, partially unknown, right? When we talk about unknown algorithms, we have partial information of those algorithms, but not 100% information, right? Yeah. Large part unknown, but small portion known, right? Small portion known, right? So we can use that small portion of known information to study the whole unknown algorithm. That's the idea, right? Yeah. So discover some common property. Those unknown algorithms may have some common property. Okay? That's the critical step. Common properties for all those algorithms. Yeah. They share some common properties, but we need to find those common properties. If you cannot find those common properties, then you cannot study. Okay? So if you can find common properties covering all those unknown algorithms, then you can study and make your conclusion. Here, we will do in that way. Common properties. All right. So let's do in that way. Yeah. How to convince people that our algorithm is optimal. Yeah. So this is we really need to understand the problem well. All right. Okay. Yeah. And here we need some imagination. Yeah. So here, because we need to make a story. Here, when we convince people, we need to make a convincing story here. Yeah. Here we use our real world experience to build this convincing story. Okay? Yeah. How to build that convincing story? Yeah. So based on it, so playing sports games to help us do the understanding, some background experience to help us, make that story. All right. Comparison. The basic operation we study in our algorithm context is comparison. In sports game, we want to connect. So in sports game, we have the similar activity, right? So when we, play a match between two players, there are several different states, right? The results could be less, if comparison less than, then there is a win, right? Something like that. Okay? Equal, tie, greater than, But here, why less than we put a win, greater than we put lose? Because our goal, we want to find the minimum, right? Minimum means the smaller the value, the better, right? At the end, when we get that global minimum, that is the final winner, right? The global minimum is the final winner. So for that reason, so the smaller the element, the better. So we treat it as a win. The smaller element beats a larger element, right? In that, connection, interpretation, in that way. All right. But here, in our real world sports games, actually, although we make that connection, but still there is some important difference between our real world experience and our comparison here. Because when we do comparison, there is an important property we can use, this transitivity property. Transitivity property is always true in our comparison operation. Always true. So what's that transitivity property? PA greater than PB. Okay? Player A is greater than player B, and PB greater than PC. If these two algebraic inequalities hold, then we automatically have the third inequality. PA must be greater than PC. That's the transitivity property. In algebra, it's true. It is always. So we can apply this transitivity property, all right? But in the real world situation, when people play sports games, it's not true. Okay? If player A beats player B and the player B beats player C, it is not necessary player A can beat player C, right? It happens frequently. So in a real world situation, we cannot apply transitivity property. Okay? All right. So, but here, we really need to use the transitivity property. Okay? All right. So in our discussion, we should be very careful because we need, the main property, the key property is this one. All right. Next, now we need to build our story. Okay? All right. So when we build our story, there is another important phenomenon we need to observe in our discussion. That is, we allow indirect comparison. Now, this concept, indirect comparison, not direct. So when we do comparison head to head, that's direct comparison, right? A and B. But based on the transitivity property, this transitivity property tells us there is a possible indirect comparison based on transitivity property. So we need to, get that understanding. So what's that? So look at here. PA greater than PB. There is one direct comparison between PA, PB, right? Yeah, that's direct comparison. PB greater than PC. There is one direct comparison between PB and PC. Okay. Then we can make conclusion PA must be greater than PC without a new comparison, right? Yeah. So after we know PA greater than PB and PB greater than PC, then we can make our conclusion immediately that PA greater than PC without any new comparison. So here we call between PA and PC there is an indirect comparison. We do not need to do direct comparison, okay? Not necessary. Because we already have the information we need. So we can save one comparison. Yeah. But sometimes when we talk about the relationship between PA and PB, we want to call it PA beats PC by indirect comparison. Okay? Not direct comparison. Okay? Although no direct comparison, but we can call PA beats PC based on our transitivity rule. Okay? Although this rule is not available in the real world situation, but in our algorithm context, it is available. So we need to apply this transitivity property. Okay? So we have this indirect comparison concept. Okay? So with that understanding, now we are ready for the story, a sequence of arguments to make our convincing story. Yeah, so let's do it step by step. All right. We need to make sure each step is correct. Okay? Yeah, otherwise, we cannot move to the next step. So each step we need to really make sure there is no any logic reasoning problem. Okay, all right. The first step, imagine that min is the final winner. Yeah. So that's the setup. Okay? Yeah, setup. Yeah. So yeah. Final winner, our goal, we want to find the final winner. Yeah. All right, for this min variable. All right. Second step. This final winner needs to beat all the other elements in the array through comparisons directly or indirectly. Yeah? So is it true? Directly, no problem, right? Yeah. But we allow indirect comparison. If the mean, this value beats a few other elements indirectly, no direct comparison, indirectly, that's still okay, right? Yeah. So this statement is correct. This statement is correct. Right? Yeah. So no problem. So we can move to the next step. Yeah, indirectly. Yeah. This time, yeah, we add. Next step. If an element loses once, it is eliminated. Yeah? This is another important statement. Here, and move here. Okay? If an element loses just once, then it has no chance to be the minimum, right? It cannot be the minimum. Okay? Yeah. Because it is greater than at least one element. How can it be the minimum? Yeah. So this statement also correct. If it loses once, it is eliminated. Okay, all right. Yeah. So here we use this word, eliminated. Yeah. Later, yeah, we will use this idea many times. We call it elimination method. Yeah. We need to eliminate certain elements from the consideration to simplify our current problem. Later, this method is one of the most important methods in this class, elimination method. Yeah. All right. Yeah. So now, let's move to the next step, next statement. Yeah. All right. Each comparison can only eliminate one element. Yeah. So, do you feel this statement all right? Yeah. Each comparison can only eliminate one element. It cannot eliminate two elements. Can you imagine one comparison eliminates two elements? After the comparison, both eliminated. Winner, so in other words, winner also get eliminated. Is it possible? Winner also get eliminated. Winner. In the real world, it's possible. Yeah, real world, football, soccer. Yeah, the winner got eliminated. Yeah. The World Cup. Yeah, the winner got because the rules, right? Some absurd rules. Yeah, ridiculous rules. But here, because the real world, that kind of thing, we do not have that part. So in our discussion here, we consider, ideal situation. In this ideal situation, think about it. So you only look at the comparison. When you compare two elements, one is greater than the other. Yeah. How can you convince people the smaller element has no chance to be the minimum? Yeah, think about this statement. Yeah. You do one comparison between two elements. Before the comparison, you have no information which one is. We need to assume both elements have a chance to be the minimum. Okay? Before comparison, both elements have a chance to be the minimum. Then after one comparison, one is greater than the other. Can you say both elements after this comparison, they do not have a chance to be the minimum? You cannot, right? You can say the larger one has no chance, but how can you say the smaller one has no chance? You cannot, right? Yeah. So based on that understanding, we can say each comparison you can only eliminate one element. Not both, not two. Okay? Not two, not both. Can you see that? Yeah. The, logic reasoning, yeah. But here, to be more accurate, I want to add a little bit. To be more accurate, I want to add something here. Each comparison can only eliminate at most one. Slightly better. Why at the most? That means eliminated zero. Okay? Eliminated zero. Yeah. So this situation is useful. How can I say eliminate zero before comparison? Because this corresponds to the situation in our real world programming. Yeah. Different programmers write different programs, but many times people can write bad programs, right? Yeah. When people write bad programs, so they waste quite some operations, then it could happen. Yeah, because when you do one redundant comparison, you do not get any useful information, right? Because you make a redundant comparison. Okay, yeah, you messed up. Okay, you couldn't track about keep track of your data correctly. Okay? You do some comparison, but this comparison does not generate any useful information. So you waste this comparison. That could happen in the real world programming. Okay? Yeah? So that's why I put at the most one. Yeah, because 0. There's a possibility 0. Okay? Yeah. But it cannot be more than 1. The point is, the best you can do, you eliminate just one element, not 2. Yeah. Okay? All right. Then the next statement. Yeah. All right. That's the last statement. Yeah. All right. We need to make our conclusion. Because our goal to get a minimum, the minimum we know, the minimum always eliminates n minus 1 elements, right? Yeah. The minimum must eliminate n minus 1 other elements to be qualified for the final winner, right? Yeah. Then you can convince people, yeah, this is the final winner. Yeah. But each element, you need to use at least one comparison, right? Yeah. Otherwise, how can you eliminate one element? So at least one comparison is needed. But to eliminate n minus 1 elements, you need at least n minus 1 comparison, right? Yeah. Yeah. The most efficient way is one comparison eliminates one element. That's the most efficient way, right? So n minus 1 comparisons eliminate n minus 1 elements. That's the most efficient way. You do not waste any comparison to get a final winner, right? Yeah. So now you can see after this sequence of logical reasoning statement, at the end, you get the conclusion. Yeah. The best you can do to find the minimum of an n element array is n minus 1 comparison. You cannot do better than this. Nobody can do better than this. And our current algorithms, we achieve this efficiency number, right? Yeah, we achieve it. We make it. Yeah. So you can tell people, yeah, this algorithm is optimal. Nobody can improve it. Yeah. Even those unknown algorithms cannot beat this one in future. Yeah. Okay? How about this optimality problem? Yeah. Optimal. Yeah. So, this problem, this question, very simple. Yeah. Finding the minimum. Yeah. For other relatively hard questions, then do this kind of proof. Also very hard. Yeah. Also very hard. Yeah. But here just let you feel about it. Yeah. How hard you need to do to answer the optimality question of an algorithm. All right. Yeah. So we complete this topic. Next, D.2, we want to apply that finding the minimum, that solution to solve another problem. So this problem is finding both maximum and minimum simultaneously. Yeah, let me describe the question. Find both maximum, minimum simultaneously. Yeah. So what do you mean simultaneously? Yeah. Let me describe the question. Given an array with n distinct elements. Yeah. So here we put this distinct word. We try to make the discussion easier. Otherwise, you always need to consider the equality situation, right? Equality. Here, we don't want to consider the equal case. So we put this distinct word there. Yeah. Question: how to find both the maximum and the minimum simultaneously? Yeah. Here, let me explain this simultaneously a little more. Yeah. Yeah. So suppose we have some algorithm to find a solution. Okay, yeah, find a solution. Yeah. So when we run this algorithm, the output is both maximum and minimum. Okay? Yeah. Yeah. We run this algorithm just once. We call this function once. And it produces both maximum and minimum simultaneously. Okay? It's not we run this function twice. The first time minimum, second time maximum. Not that. Okay? All right. So we only call this function once, and it generates maximum and minimum. Okay? Yeah. And we also need to count the number of multiplications, and we want to get the smallest non-multiplication comparisons. Yeah. And we want to get the smallest number of comparisons. Okay? That's the goal. Yeah. Yeah. So it's not, yeah, a little harder, yeah, a little harder than the previous one. Yeah. All right. So let's look at the solution here. Yeah. All right. Analysis. Yeah. We need to understand our data. Data. Okay. All right. N elements. We use x1, x2. Yeah. Notations. Yeah. All right. So now we need to try to, understand this elimination method. Yeah. So elimination method is very useful. Yeah. The idea is so simple, yeah, but very effective. Yeah. If you use this idea in your real-world problem solving, very effective. Yeah. Here, let me explain some properties of this method. When certain elements do not satisfy the criteria. Yeah. For example, you need to determine some special element that satisfies certain criteria. For example, it must be the minimum, it must be the maximum, or it must be the median. Yeah, median. Yeah. So later we need to do a lot of questions regarding the median, finding the median. Yeah. Yeah. If certain elements have no chance to meet that given criteria, right? Yeah. Then we can eliminate them from the consideration. Yeah. Take away. Okay? Remove from consideration. Although it looks like trivial, right? Yeah. Why so important? Yeah, actually, you will see many problem solvers. So we treat ourselves as problem solvers. Many problem solvers forget to remove those irrelevant elements. Yeah, those elements, because after some comparisons, they are irrelevant. They have no chance to be the final solution. So they are irrelevant. But some problem solvers still keep them in the consideration. Okay? Then you may do redundant comparisons. When those irrelevant elements are involved, you do redundant comparisons. You don't like to do redundant comparisons, right? So you waste a lot of comparisons on redundant elements. Yeah. So that's the problem. Yeah. Then, after we eliminate them, why we can do better? Because we use this principle. Yeah. Later we will call this principle. What's that principle? Since the data size is reduced, yeah, when you remove those irrelevant elements, you reduce the data size, right? Yeah. The number of elements in the array, we call the data size. So you reduce the data size. Then we can achieve better efficiency. Here we use the principle, the smaller the data size, the easier the problem, right? So here we use, this is a principle, okay? Later I will explain the principle. What's the meaning of this principle? What's the meaning of principle? Okay? Yeah? Yeah. All right? Yeah? Yeah. Later at the right time, I will explain this. Yeah. Here we treat it as a principle. Yeah. Yeah. All right. Notation. Yeah. So here we do some notation. When we do comparison, yeah, sometimes we do not want to write long sentences. Okay? Yeah. So we use some short symbols, yeah, sometimes. Yeah. So notations. Yeah. So compare xi and xj, and xi is the winner. So we write this way. Okay? Yeah. Xi is the winner. Yeah. Yeah. All right. Yeah. But the default winner, yeah, here, default, if we do not say anything special, specific. So default winner, we mean the larger element, okay? Yeah, not smaller element. If you want to make smaller element as the winner, yeah, you should say it, okay? Yeah, so that's your rule, okay? You need to tell people your rule. Yeah. If you do not tell people what is the rule, then by default, people treat the larger one as the winner, okay? Yeah, the default case. Yeah. All right. Yeah, based on requirement. All right. Now, let us do our data manipulation here. Yeah, we need to work on the data. Okay. Yeah. All right. Yeah. So here, the question: how do we organize our data for comparison? Well, so there is a data organizing step. No. We need to arrange the data in a well-organized way, yeah. Not some messy way. Okay? Yeah. Yeah. So that issue. Yeah. Yeah. All right. So here we use one commonly used way: group the data in pairs. We pair our elements. Group the data in pairs. Yeah. Later we will call it tournament method. Okay? Tournament method. Yeah, tournament. Yeah, tournament method. Yeah. Another, real world. It comes from the real world experience. Yeah. Yeah. So you play the sports game in the tournament fashion. Yeah. Right? You pair the players. The first round, all the losers are eliminated, so the winners move to the next round. Then you pair the winners for another round, winners, losers. Then at the end you get a final winner. That method, okay? The tournament method. All right, so let's pair all the elements. Okay, all right. All the elements, but we need to consider even and odd case. For odd case, the last element cannot be paired. Last element cannot be paired. All right? Yeah. All right. Yeah. So we need to consider these two cases: even case or odd case. Yeah. Here, when we have two cases to be considered. Yeah, so here, two cases to be considered. There is a question. Which one we should consider first? The answer is we always work on the simplest case. Yeah. Because these two cases, usually one is simpler than the other. Yeah. So we have multiple cases. Yeah. Our problem-solving strategy is you always work on the simplest case first, not the hardest case first. Okay? Yeah. Simplest case, always simplest case first. Yeah. So here, which case do you feel simpler? Even case or odd case?
Even.
Yeah, even simpler. Yeah. Because all of them are in pairs. Okay? Yeah. All right. Yeah, let's work on the even case first.
This is only for like one-to-one comparison, right?
One.
This is only to a one-to-one comparison.
Yeah.
If you have one-to-one-to-one comparison.
Yeah.
That would be pairing your groups with three.
Yeah. One to one. Yeah.
Yeah.
Yeah. Yeah. All right. All right. So here, now let's talk about this tournament method. All right. Now, pair the players, even case, odd case, and we want to work on the even case. Yeah. Yeah. So let us use diagram. Yeah. The first round. Yeah. First round. Right. So let's draw the diagram for the first round. Okay. One comparison between x1 and x2. Okay. Yeah. Then another comparison between x3, x4, and so on. Okay. Yeah. The last comparison between the last two elements. All right. Then, for each comparison, we want to get a winner. Okay. Winner. Each comparison. All right. There are two cases, right? Because x1 could be the winner, or x2 could be the winner. So there are two cases. Yeah. For each comparison, there are two possible cases. Second comparison, also two possible cases. Each comparison, two possible cases. Okay? All right. Yeah. Yeah. How many total cases? How many total cases?
7 cases before there's just the first round or in total? There's 4 in the first round.
N is unknown. N is unknown. N could be 1 million. N could be any even integer. N must be even integer.
So n cases in the first round? N cases in the first round?
Yeah, first one. Yeah, so how many possible comparison results for the first round after the we'll do it. Yeah, good. Yeah, yeah. N over 2, that's the number of pairs, right? Yeah. N over 2, that's the number of pairs. For the question, this N over 2 number of pairs. But in your discrete method, you do the counting. You count the number of comparison results. In this situation, you know the number of pairs, this number. Do you still remember how to do the counting? Basic counting in your discrete math? There is certain method, counting method to use. Okay? Yeah. Multiplication method. When you combine all these cases, how do you combine? In this situation, current situation, multiplication method. Here, you only need to ask. So because when n is large, it's too complicated, right? Now, I make it simpler. And if I cover all the remaining pairs, you only consider 2 pairs. How many total pairs, total possible results? 2 cases here, 2 cases here. Combine them. How many? First pair, you have 2 possibilities. So, another 2. Combine 4. 4, you have 4. Do you do 2 plus 2 or 2 times 2? How do you get that? Because 2 plus 2 is 4. 2 times 2 also 4. So which way you use? Yes, 2 times 2. 2 times 2. Not plus. Okay? Not plus here. The reason is any of the 2 cases here is irrelevant. Has nothing to do with any of the cases here. Okay? So you can do whatever you like here. You can do whatever you like. There is no connection between the 2. Then, when you combine, you use the multiplication method. If there is a connection, yeah, when you do one particular, the result will impact the second pair. In that situation, you do not do multiplication. Okay? You do addition. Okay? You do addition. Yeah. So that's from your discrete math. All right? Yeah. So here, we do multiplication all the way from beginning to end. So the answer is 2 to the n over 2. This many total cases. Huge number, right? Think about it. Yeah. When n equals 1 million, that's a huge number. So you don't want to exhaust all the possible cases, right? Nobody wants to exhaust all the possible cases. So how do we deal with the situation like this? We don't want to, Yeah. So under this situation, what's the best way we should do? We want to do a simple way. We don't want to do, very messy way. All right. All right. So here, let me tell you the best way we are going to do for this class. Only do one way. No matter it's 1 million, 2 trillion, 3 billion, yeah, it doesn't matter. We always do one way. Why one way? One way can represent whatever that number, because x1 is the winner, x2 is the winner. What's the difference? Is that difference important? Not important. Just the one is winner, the other is loser. If we make x1 winner or x2 winner, just a flip between 2 elements. We just choose one of the 2. That's good enough, right? Because the difference is just you flip, you switch 2 elements. That difference is not fundamental. Okay? So we just pick one of the 2 symmetric, because these 2 cases are symmetric. Okay? When you do symmetry, same thing. Okay? When you do some symmetric operation, okay? Put a mirror here, flip along the mirror here, same thing. Okay? Yeah. Here we just use the symmetry property. All right? If it's not symmetric, then you cannot do it this way. So here, perfect symmetry. All right? So each case we pick a representative. Yeah. It could be x1 the winner, x3 the winner. Yeah, we just pick one of the 2 cases. Yeah. So at the end, we only need to consider one case. Yeah. All right. Yeah. All right. So here you can see, we only use one typical case as the representative covering all the possible cases. If you can find the symmetry property, here we have the symmetry property. Because sometimes we do not have the symmetry property. Okay? Yeah, let me draw an example that you do not have the symmetry property. Okay? All right. x1 here. Okay? x2 here. x3 here. Okay? x3 below x2, that means x2 is greater than x3. Okay? Now you do comparison between x1 and x2. There is a winner. In this situation, it's not symmetric. Okay? x1 is the winner. it's quite different from x2 is the winner. Okay? So in this situation, you need to consider two cases. Okay? Yeah, because it's not symmetric, right?
I was thinking two cases, you pick a winner, then you
Yeah.
fight through later.
Yeah. Yes. But what do we have here? Symmetric. Symmetric, we just consider one of the cases. Right? Yeah. Yeah. All right. Next. We need to look at the result of the tournament method. Yeah. All right. Yeah. So when we go to the result, so here we make assumption. Okay. Yeah. We assume x1 is the winner of the first comparison, x3 is the winner of the second comparison, and so on. Yeah. Yeah. So we can do discussion easily. Yeah. So we get to the, yeah. So usually, so people, we assume this kind of thing without loss of generality. Yeah. Because for other cases, we can easily, you know, the same situation. We just do appropriate mapping. We can cover any case, any of the cases. Certain mapping, right? Yeah. So here, yeah. Here you can see we use our abstraction in our mind. Abstraction. We need to do a lot of abstraction in thinking. Yeah. Yeah. All right. Now, yeah. So here. Yeah. Now we do the following discussion. Yeah. So, you know, from this first round comparison, yeah, we need to show people the current state. Yeah. X1 is greater than X2. Yeah. So we draw this diagram. Yeah. Yeah. Higher one is greater, lower one smaller. Yeah. I mean, visual understanding. So this is visual understanding. Okay. All right. X3 greater than X4. Yeah. And so on. Okay. Higher. So then we want to do data characterization. Remember? Data characterization. Yeah. In our chessboard question, you know, yeah, characterization is important. Put our data in different categories. Yeah. So the data, the elements in the same category, they share some common property. Here, we want to use, you know, data grouping, character, yeah, same thing. Yeah, put the like elements in the same group. Yeah. So those elements, they share some common property. Yeah. So we put them in the same group. All the top elements, we put them in one group. Yeah. So we call it winners group because they are all winners. Okay? Yeah. Winners group. Yeah. The bottom elements, another group, so losers group. Yeah. So they share the same property, right? All winners, same property. All losers, same property. All right, yeah? So when we do processing, we need to use these two common properties. Yeah. All right, next, we need to apply our elimination argument, elimination method here. All right. All right. Think about when we find the maximum, which group should you work on? Okay. Maximum. Winners group or losers group? Maximum.
What's the winners?
Winners group. Yeah. How maximum can be a loser, right? Yeah. So in this way, you can see with these two groups, you can automatically eliminate 1/2 of the elements from the consideration without doing anything, right? Yeah. So here, after you group them, you do not need to do anything. You can already eliminate all the losers when you find maximum. Maximum, you only need to do the comparisons in the winners group. Similarly, for the minimum, you only need to do comparisons in the losers group.
But we have like a binary search for this.
Binary search,
Defines the group that's supposed to be in,
yeah,
and that's the winner group. You can't compare.
not going that far. Okay, binary search. Do you mean how to find a maximum in this group?
Yeah.
Yeah. Remember, we just did that, finding the minimum, finding the maximum. And we already know that algorithm is optimal. Why not just apply that optimal algorithm? You already have optimal algorithm, right? Nobody can do better than that. Even use binary search, whatever, sophisticated algorithm, you can never beat our optimal. Yeah, we have optimal solution. Yeah. All right. So let's get a final. Yeah. So now we are ready to get a final solution. Yeah. Maximum only appears in the winners group. Minimum only appears in the losers group. Now we need to find them. Yeah. Apply our solution of problem number 4, the previous one. Yeah. Elimination. Yeah. So here we already. Yeah. So we did the elimination wheel. Okay? Yeah, we complete that elimination understanding. Yeah. All right. But this time we need to do the counting. We want to count the final total number of comparisons. We do counting. The first round, n/2 comparisons, right? Yeah. Yeah. So first round. Yeah. Then to get the maximum in this group, the total number of elements, n/2 minus 1. Yeah, that's our, previous solution, problem number 4. And losers group finding the minimum, n/2 minus 1. Okay, yeah. Add these 3 numbers, 3 subtotals to get total number comparisons. Yeah. 3n/2 minus 2 comparisons. Yeah. Yeah. So, all right. Yeah. So we near the end. Yeah. Yeah. So I just want to say last sentence before we leave. Yeah. That is, this algorithm is also optimal. Okay? Yeah. The best. Yeah. Optimal. And it can be proved. Okay? It can be proved. Yeah. But the proof is, pretty much harder. Yeah. Much harder. I can give you the reference book. Okay? Yeah. The book page reference. Yeah. Okay? Yeah. All right. Yeah. So still we have the other case. Yeah. But the other case is similar. Okay. Other case similar. Yeah. All right. Yeah. That's it. Yeah. So we finished module 1. This week I will post our quiz number 1, covering whole module 1. Okay. Quiz number 1. The weekend, but you have 1 week to complete it. Okay. So the deadline is the end of next Sunday. Yeah. More than 1 week.
Posted this weekend.
Yeah, this weekend, Friday, Saturday. Yeah.